All right, so our three main states of matter: solid, liquid, gas. You guys have a Venn diagram to review some of those properties that I know even my second grader is covering differences between solids, liquids, and gases. So I don't think it's anything brand new in terms of information. All right, so let's focus on maybe some of the newer stuff, beginning with what's called the kinetic molecular theory. The kinetic molecular theory is a theory, right, that is explaining the structure, arrangement, movement of particles, right, for our different states of matter. Remember, theories in science, these are highly supported, investigated, researched, evidence-based, right, explanations. Takes a lot to get to this status to call it a theory. And so this theory in particular, again, is focusing on particles with our different states of matter. A lot of it does have to do with gases, but some of them do apply to all of our states of matter. So let's jump in with the first one, kinetic molecular theory. Gas particles. Gas particles are tiny and separated by lots of empty space. Gas particles are tiny and separated by lots of empty space. The significance of this statement is about measuring the volume of a gas. When I measure the volume of a liquid, I'm talking about water a lot today, measure the volume of liquid, measure the volume of the solid. You are measuring literally the space that the atoms are filling up, right? How big are the atoms? How many atoms are there? That's telling you the volume. But that's not the case with the gas. The particles of the gas are so small and there comparatively is so much empty space between them that whenever I measure the volume of a gas, I'm just measuring empty space. That's what we're saying. The volume of a gas is the empty space between the particles. The particles themselves, if I actually measured their volume, is so tiny, we say that it would be negligible, meaning so small it doesn't even count, it doesn't even matter, right? So that's what we're saying with number one. Gases, their volume is mostly empty space, right? All right, next thing. Gas particles are in constant, random, rapid motion. Gas particles are in constant, random, rapid motion. So I like to demonstrate this for students. I use a model of sorts with my fists, right? In this scenario, each of my fists represents a different particle of a gas. And so if I were to illustrate for you the movement of gas particles, it might look something like this. Constant, random, rapid motion, right? That's how gas particles are behaving. Now this one also applies on some level to solids and liquids because every state of matter have particles in motion. If I were to use my same hands for a liquid, in a liquid, the particles are attracted, they're close to each other, but they're not locked in place. They're free to flow and move past one another, right, throughout their container. That might make sense. Water flows, right? We know how rivers work, things like that. But even with your solids, right now with your solids, they may not be flowing like we think a gas and a liquid can, but in their locked positions, they vibrate. That's a type of motion. It may not be from point A to point B, but it is considered a type of movement through those vibrations. So all states of matter are in some kind of motion all the time, right? Even if they're not going from point A to point B, which is what we think of with flowing. The solids do vibrate, right? All right, so that's second part, kinetic molecular theory. Third part, the kinetic energy. The kinetic energy of particles is directly proportional to temperature. The kinetic energy of particles is directly proportional to temperature. So with that, we're going to take a time out because we're going to make sure we now have an official chemistry definition for temperature. Temperature is defined as the measure of the average kinetic energy of particles in a sample. The measure of, that's an A, the measure of the average kinetic energy of particles in a sample. So we've used this word kinetic energy twice now, back in KMT and now down here. So let's make sure from our physical science course. Kinetic energy is a type of energy, and it's often described as the energy of what? Energy of movement, energy of motion. Things that are moving possess kinetic energy. So we think in the tortoise versus the hare. The tortoise has a little bit of kinetic energy. The hare has more kinetic energy. The amount of kinetic energy is related to how fast it's moving. The faster it's moving, the more kinetic energy it possesses, right? So when we talk about temperature here, we're saying, hey, when I measure the temperature of this water, what I'm doing is I'm measuring how fast the particles are going. But there's a catch, because all the water molecules are not all going the exact same speed all the time. So that's why we got to throw this word in here, average. It's an average kinetic energy of the particles. Some water molecules going really fast, some going slower, and they can change those speeds over time, right? How fast or slow they're going when they run into each other. And so coming back here to KMT, all this is saying is, hey, if my temperature goes up, what happens to my kinetic energy? Temperature goes up, kinetic energy goes up, because it talks about being directly proportional. This is why you'll hear me say, people say, oh, if I heat up the water, the particles are going faster. Because I know if I heat it up, its temperature goes up. If the temperature goes up, its average kinetic energy goes up. And if the average kinetic energy has gone up, then on average, your particles are going faster. Right? That's the connection that we're making here. The temperature is related to how fast the particles are moving. Higher temperatures, faster moving particles. Right? All right, next. Gas particles. Gas particles collisions, possessive here, with objects. Gas particles collisions with objects. They are completely elastic. Completely elastic. E-L-A-S-T-I-C, like a rubber band, elastic. This is actually in contradiction to most collision. Most times when things collide, I think of playing pool, billiards, right? You transfer some energy around by hitting the cue ball, which hits the other ones. But eventually, how do you know when it's the next person's turn? When everything stops, right? When everything stops on the table, then it's the next person's turn the next time to take a shot, right? And that's because normally when you have collisions, over time things will slow down. Meaning over time they will lose energy, right? That's not the case with gases. Gas particles, when they collide, they never lose energy. That's not to say they can't transfer energy. So if a fast one runs into a slow one, the fast one can transfer some of its energy to the slow one, much like playing pool. But think of pool where the billiard balls never stop moving. They keep going the entire time, perpetually, right? They never stop. That's what it means to say that the collisions are completely elastic. I like to think of it as the Energizer Bunny. They just bump into stuff and keep going. Right, with no concern for how much energy, right, the energy is conserved. We say here no, and I'm using a capital E for energy. No energy is lost. Guys, there's great evidence that this is true. Right now in this room, has it ever started raining on us? No. Even though there's water vapor in this room, maybe not a ton, but there's water vapor in this room, at no time did that water vapor ever stick together and form water that would fall on us. Nor does that happen with the oxygen in this room or the nitrogen in this room. We don't have liquid nitrogen raining down on us in this room spontaneously. That's because the particles are always moving. If they were to start slowing down, then they would stick together and form liquids. And that doesn't happen. We don't have spontaneous condensation just in a typical setting. Yeah, I know we got clouds, and that's different. That's weather stuff, right? Clouds that make rain, but not just like in a room here. All right, last thing with KMT. Gas particles experience no attractive or repulsive forces. Gas particles experience no attractive or repulsive forces. As we mentioned yesterday, Solids and liquids definitely have attractive forces. That's why they're sticking together in the first place. It's just about how strong they are. The solids, they're so strongly attracted, they can't even move around anymore. Liquids, they're attracted but can move around. Gases, none. Which means how they move, where they're going, never influenced by anything else. Sometimes if water molecules get close enough to each other, like if we spill water, they want to get together. That's why water will bead up when you make spills. It makes small little puddles, little beads of water. They want to stick together. Gas particles, nope. They don't want to stick together. They don't care. They don't even realize that there's other things around them. So I like to think of gas particles as crazy Energizer bunnies with blindfolds on. They just go all throughout the room all the time. Yeah. All right. All right, so that's our KMT, and we use this a lot to explain some of the other observations that we see with our states of matter. Specifically, there's a lot of stuff here with gases, and our whole next unit is on gases. So we'll actually come back to this for why some of the calculations are the way that they are. Okay? All right, now we're going to shift our focus onto temperature again. Temperature, average kinetic energy. The Kelvin scale is the SI unit for temperature. And there will be times we have to put our temperatures into Kelvin in order to do calculations. But I will agree with you, Celsius thermometers, that's still the standard, right? If we need to measure temperature in the lab, we're getting out a Celsius thermometer and doing that. But Kelvin is the official SI base unit. Part of that is how the Kelvin scale was developed. The Kelvin scale is developed entirely on the idea of absolute zero. Absolute zero would be 0 Kelvin. That is where the scale was set. They made sure that 0 was absolute zero. And absolute zero is the lowest possible temperature of anything. And if that's the lowest possible temperature of anything, that means that your atoms, they're going to possess, am I spelling possess right here? They possess the lowest, actually I'm going to say they possess no kinetic energy. If temperature is the measure of kinetic energy, then absolute zero is the absence of kinetic energy. Right? They possess no kinetic energy, and in that case we would say that all particle motion ceases at absolute zero. It stops. Nothing is moving, nothing's vibrating, right? It'd be a solid at that point for most things. No particle motion. And that was the entire basis of the absolute zero scale. They're like, hey, why don't we make zero the actual lowest temperature that we could ever have? Makes sense to me, right? Other nice thing about this scale, that means there's no negative numbers at all. Sometimes that's why we need to use it for math, because we need to make sure that every possible temperature has its own unique number, and we don't want to have a positive 20 and a negative 20 for a calculation, right? So we'll use that too. So we're going to compare the temperature scales here. Fahrenheit is in this picture only for FYI, because you guys get curious. We use it a lot. In science, though, we stick with Celsius and Kelvin. You will never be tested on Fahrenheit. It's just there for curiosity. All right, on this diagram, these 3 lines represent 3 specific locations. The top line is going to represent the boiling point of water. The middle line is going to represent the freezing point of water. And then the bottom line is going to represent absolute zero. And so I just want to get a comparison side by side so you can see how these temperatures shape up. Let's start first with the Celsius scale, because I think you guys are pretty good with that one. Hey, what temperature does water boil at in the Celsius scale? 100. 100 degrees Celsius is the boiling point. What's the freezing point in Celsius? 0. And guys, that was the basis of the Celsius scale. It was created based on water. They said wherever it freezes, we're going to make that 0. Wherever it boils, we're going to make that 100. And then we're going to split it up equally between those two. Right, and go from there. All right, let's go to Fahrenheit. What's the freezing point of water in Fahrenheit? Now, I know we don't see it that much, but every once in a while they get really excited when we drop into the 30s in Florida. We're going to have a hard freeze. Okay. So it's 32 Fahrenheit. What about boiling in Fahrenheit? 212. And then they split this up in between. I do, at some point, your textbook might have what the Fahrenheit scale was based on. It was like on room temperature and like body temperature is where they set some of the stuff for the Fahrenheit scale. Hey, looking here, how could I compare 1 degree Fahrenheit to 1 degree Celsius? Which one's bigger? 1 degree Fahrenheit or 1 degree Celsius? It's going to be Celsius. This only gets broken up into 100 pieces. This gets broken up into like 180. Yeah, so 1 degree Fahrenheit increase in temperature doesn't go up as much as 1 degree Celsius. It's a different change in energy, more energy change for the Celsius. All right, so now let's jump over to the Kelvin scale, right? Our Kelvin scale based on absolute zero. That is 0 Kelvin. Notice the lack of a degree sign, guys. No degree signs in Kelvin. It's 0 Kelvin, not 0 degrees Kelvin. And so moving up here, the freezing point of water in the Kelvin scale is 273 Kelvin. No degree sign, just 273 Kelvin. And the boiling point of water in the Kelvin scale is 373 Kelvin. So once again, compare for me 1 degree Celsius and 1 Kelvin. Who's bigger? 1 degree Celsius and 1 Kelvin? Not 1 degree Celsius. Not 1 Kelvin. Trick question. They're the same, guys. See how the difference here is 100 and the difference here is 100? That means every little increment would be the same amount. So this is actually super convenient for us because when we often take our measurements in Celsius, we have to convert them into Kelvin in order to do our calculations. And 1 Kelvin equals 1 degree Celsius, so the conversion is really simple. If you ever want to look up the conversion to go between Fahrenheit and Celsius is awful. It involves some version of either 9/5 or 5/9, and then you are either adding or subtracting 32, depending on which direction you're going. And it's annoying. But if I want to do this conversion, a temperature in Kelvin is equal to its temperature in Celsius plus 273. And so you will have to do this. This will be on your test. It's on a worksheet to go back and forth between Celsius and Kelvin temperatures. All right, finishing this off, just so we can fill in for informational purposes. Absolute zero in the Celsius scale, that would be negative 273 degrees Celsius, because I would do 0 minus 273 to get the Kelvin temperature. And then the absolute zero on the Fahrenheit scale, totally random. I did the math one year. Negative 460 degrees Fahrenheit. Negative 460. Yeah, we're not getting there. I mean, not like weather-wise. Okay. Hey, guess what? This formula right here is on your formula sheet. If we go to R6, just FYI update, you didn't need it for the last test, but hey, look, there's the percent yield equation if you ever needed it. But now coming down here, hey, there's our conversion for Kelvin and Celsius on your formula sheet. All right, so now, when we start talking about phase changes, that's where we're going to be going. We got solid, liquid, and gas, and now we want to start talking about the phase changes for them. In order for these phase changes to happen, we usually are manipulating energy, right? We are either adding energy or pulling energy away from our substances in order to get them to freeze or to boil or to melt or to condense, right? And we have words for that, for which direction the energy is moving. It's called endothermic and exothermic. You can remember thermic, like thermal energy, heat, right? And then endo going in, exo going out. Exo like exit, right? Endo inside. Okay, so let's define these words and then let's apply them to our different phase changes. An endothermic is a reaction or process that requires, put it all caps for emphasis, or you might also hear the word absorbs energy. So a reaction or process that requires or absorbs. Energy has to go into that sample in order for that thing to happen. So I always use water, right? Ice, liquid water, and water vapor kind of to help me think about this. And I think about, do I have to heat it up? Do I have to put heat in to make this thing happen? So we've got melting and freezing, right? Which one would I have to heat my sample to make happen? Melting or freezing? Do I heat something up to freeze it? No. Do I heat something up to melt it? Yes, that's why melting will fit under here as an endothermic process. Right? Our other phase change between liquid and gas, we've got boiling and condensing. Boiling and condensing. Which one would I heat up to make that happen? Boiling, right? I boil my water. I put my water on the stove. I'm heating it up. Boiling is an endothermic process. Now there's one more phase change that might be new for some of you. There is a phase change that takes you directly from a solid to a gas, and you skip the liquid in the middle, going from solid directly to gas. Anybody know the name of that phase change, solid to gas? All right, well, we're going to put it in our notes now. Solid to gas is called sublimation. And please write in there, solid to gas. I just use S to G, S for solid, G for gas. You will have to know that for your test, that sublimation is solid turning into gas. So solid to liquid, liquid to gas, solid to gas. Anytime you're going in that direction, solid, solid, liquid to gas, those are going to be endothermic. Which means all the other ones are going to be exothermic. So exothermic, a reaction or process that we would say releases. Let's write that a little nicer. That releases or produces energy. Energy is exiting, leaving that material. And so these are going to be the opposite. Opposite of melting is freezing. Freezing actually releases energy because you got to take the energy out so that you can strengthen the attractions, right? You slow them down is what you're doing. Opposite of boiling, condensing. And then anybody know the opposite of sublimation, going from a gas all the way back to a solid? Well, dry ice is usually sublimating, right? It's going from solid to gas. It's called deposition. Deposition is going from a gas directly to a solid. This can happen with snow. Okay, so be willing to know the phase changes and whether those phase changes require or release energy, describing them as endothermic or exothermic. Now, there are three main states of matter, solid, liquid, and gas, but there are actually more. We are only responsible for learning a little bit about one more of them, and that's plasma. Plasma is a fourth state of matter. After plasma, it gets real advanced with the type of stuff that we're making, Bose-Einstein condensates and crazy stuff, right? All right, so here we go. If I were going to talk about a plasma. Guys, a plasma is a gas, but with a twist. It's been ionized, and if you're ionized, that means you have a charge. So I have gas particles that have a charge. That's a plasma. Gases with a charge. That's simple. So it shouldn't be too surprising then that plasmas share some characteristics with gases. Specifically here, a plasma has no definite shape or volume. Much like gases have no definite shape or volume. We can fit them in any size balloon we want, right? And we can compress them like into our scuba tanks or into our CO2 canisters for our paintball guns, right? No definite shape or volume for plasmas or gases in that case. But the fact that it has a charge on it, the particles have a charge, that does mean that it can behave differently in the presence of a magnetic field. And again, that's just because it's charged. We're trying to differentiate how are gases different from plasmas. Plasmas you can manipulate in magnetic fields. Gases you wouldn't be able to. And so some common examples of plasmas Plasmas can be found in stars, right? Those gases, but they can get ionized in there when they're undergoing fusion reactions. Do you guys remember when we did the atomic emission spectra? You guys remember hanging on my board over there, those like black rectangles that had the colored lines in them? Didn't I show you guys a video for that, or did I get out the real box? I don't even remember now. Did I have the real box? All right, cool. So I had the real box out, right? When it's off, it's just a gas in the tube. But as soon as I flipped the switch on and it started to light up like a neon sign, guess what? I was running electricity through it. I was charging the gas particles. So when the sign is on, it's a plasma. When the sign is off, it's a gas. Very much like I can take water and go between ice and liquid, right? I could do the same thing with a gas and a plasma. Flip the switch on, flip the switch off, flip the switch on, flip the switch off. It goes back and forth. Another example, lightning. Lightning will charge some particles. It's actually trying to discharge some of that electrical energy, right, with lightning. And that's really all we need to know about plasmas, just their existence, their connection to gases, but yet their differences in terms of their charges and some common examples. All right, so last section here, it's a vocab lesson, right? We talk about water vapor. That's big in Florida because the water vapor determines how humid it is, right, and the air. But have you ever heard anybody talk about oxygen vapor? Like if we talk about oxygen, they usually call it oxygen gas. But isn't water vapor also a gas? Like isn't water vapor water that we've boiled away and now it's in the gaseous form? So why do we call it water vapor, but we call it oxygen gas? The use of those two words, gas or vapor, has everything to do with how that substance exists normally at room temperature, right? So we would describe something as a gas if that's usually how it is at room temperature. Oxygen is a gas at room temperature. Nitrogen, a gas at room temperature. Helium, a gas at room temperature. Carbon dioxide, gas at room temperature, right? Those are all gases, and we call them gases. But if something was a solid or a liquid at room temperature, like water, but then it turns into a gas, that's what we call a vapor. So we have alcohol vapors, because a lot of our alcohols are liquid at room temperature. We have water vapor. And in class on Monday, guess what? I'm going to show you some sublimation where I'm going to start with solid iodine. And then I'm going to turn it into iodine vapor because it's solid at room temperature, but when I turn it into a gas, we call it vapor, right? So that's what's going on with those vocabulary words, gas and vapor. All right, so to the back. Now we're moving to our heating and cooling curves, and this is a heating or cooling curve. It's a heating curve when the line's going up. It would be a cooling curve if the line was going down, but in each case, every heating or cooling curve has the same 5 line segments. There are 3 diagonals. There are 2 flat or horizontal sections. Always. So if it were going down, you don't have to draw this, it would look like this. 1, 2, 3, 4, 5. That would be a cooling curve, still 5 line segments. Yeah. Okay. I'll often just call it a heating curve. Most of the ones we draw go up. I don't often see the cooling curves as much. Okay. So they all have 5 line segments. What can be different? Because you draw one for each substance. So water has one, carbon dioxide has one, helium has one. Like every different chemical can have its own heating and cooling curve. What changes is how long those segments are. How long or short. So sometimes this could be longer. You could also change the angle of the diagonal. That can be part of it too. But they always have 5 line segments, right? So let's label them for what they are referring to, what's going on. Notice we have temperature here. And down here, this is saying heat added. I like to think of this as like, hey, I put it on a hot plate, and now I'm just over time continually adding heat to it on my hot plate, right? So this segment right here, this represents when your substance is a solid, it's sitting on the hot plate, and you are simply heating it up, but it's still solid. So imagine I had some metal, right? Think of like your pots. My pot's put on the stove, and I turn on the stove, and I'm heating up the pot, but it's still a solid, right? That's that first diagonal. The next diagonal, that represents when you are heating up the liquid form of that substance. So I can't really use my pot example anymore because I'd have to completely turn it into liquid now. But let's just go back to water. If I had water and it was sitting on a hot plate, now it would be water. If I put it on right now at 25, it doesn't boil immediately. There would be some period of time, right, where it's warming up before it actually starts to boil. So that's that middle diagonal. And then if I had trapped the gas into a container and continued to heat it, that would be where the gas was continuing to warm up. So the diagonals refer to these states of matter. All you are doing at those times are heating them up. So then what are the flat parts? The flat parts are the phase changes. So what's it called when I go from a solid to a liquid? What phase change is that? Solid to liquid is melting. And what's it called liquid to gas? Boiling. And so this would be if I were heating my substance up. But without redrawing the whole graph, let's pretend we were going back down. What if I was going from a gas to a liquid? What would I call that phase change? Gas to liquid is condensing. And then liquid to solid is freezing. Liquid to solid is freezing. Okay. So those are the basic parts. The flats are the phase changes. The diagonals are the warming of the states. Hey guys, notice the temperature is not changing during the phase change. See, it stays right there. If I kept it at that temperature and I had it in a sealed container, you would not see a temperature change while the phase change was occurring, or even if I kept applying heat. The heat's being used differently. The heat's being used to mess with the intermolecular forces. It's not just making them go faster or slower at that point. It's changing the strength of the attractions, right? From this type of curve or diagram, curve sounds a little weird to me. Guess what? I can now also tell you what the boiling point of my substance is. 60 degrees is my boiling point. And likewise, down here, I could tell you what the freezing point is. But the freezing point would also be the same as what other point? No, freezing and condensing aren't the same. The freezing point would also be the same as the melting point, guys. They're at the same temperature. It's like going different directions through an intersection. One's going north and one's going south, but the temperature is going to be the same going from, it's just like we know water freezes at 0, but also we know it's going to start to melt when it gets above 0, right? 0 is that tipping point from solid to liquid in Celsius. Yes, I could say there's a condensing point, a condensation point. We don't talk about that a lot, so that's why I didn't label that one. And so that's why you could see if I had a different substance with different lengths of those 5 line segments, then they could end up at different temperatures for their own boiling points and freezing points. All right, 2 more things on this graph. I use heating curves to help me remember which phase changes are endothermic and exothermic. Because I know that I'm going solid to liquid to gas. Anytime I am going this direction up my graph from solid to liquid to gas, it's going to take energy to go from that slowly vibrating solid to a more freely moving liquid to a super crazy random rapid gas, right? I got to put energy in to make that happen. Plus the graph says heat added this way. Right? So that means anytime you're going this direction, these phase changes are going to be endothermic. That's going to be the melting and the boiling if I was going up. And even though it's not on the graph, that would also be sublimation, jumping from solid up to gas. But anytime I'm going this direction on the graph, gas to liquid to solid. Now I got to take it from that crazy gas and I got to slow it down to a liquid and then slow it down even more to get it to vibrate as a gas. That's going to be exothermic. Hey, fun Florida fact. We live in Florida. We got lots of strawberries around here. Strawberry Festival coming up. What do farmers do when they're concerned that their strawberries are going to freeze overnight? What do they do to their strawberries? They what? They do more than cover them. They do something else. Anybody know what they do with the strawberries? We cover stuff at our house, but what do they do with the strawberries? Again, they got giant fields. They're not covering them with stuff. They do something else on these giant fields of strawberries. Anybody know? They spray them with water. They've got the sprinkler systems there. They turn their sprinklers on and they coat them in water. And some people think that they're doing that so that it performs a protective layer, but that's not what they're doing at all. That's not really what they're trying to do. What they're doing is they're utilizing the fact that freezing is an exothermic process. So what happens is there's a layer of water on the outside of the strawberry and that water freezes, it's releasing energy to its surroundings. Yes, some of it goes out into the air, but guess what? Some of it goes into the strawberry. So by the water freezing on the outside of the strawberry, it actually, to a small extent, is warming up the strawberry on the inside. Which they're hoping, as long as it doesn't stay super cold for very long, that that's enough to keep the strawberry from freezing also. Right? So that's a big Florida connection. This comes up a fair amount. Spraying the strawberries, it's because freezing's exothermic. Yeah, there might also be a little protective layer, but it's the exothermic reaction, releasing heat into the strawberry, that really is helpful. Right? All right. So last thing on this graph, energy, right? You are adding energy in the form of heat all the time, but it's being used differently. That's what I was trying to get across with the fact that on the flat parts, the temperature is not changing. Here, when it's a solid, the heat is being used to make the particles go faster. And then as a solid, they're vibrating faster. So they're vibrating slower, and then I heat it up, and they're vibrating faster. But they're finally going to get to a point where now they're ready to start breaking their intermolecular forces, or at least weakening them. So I would say when I get to my phase change, PE stands for potential energy. The strength of the attractions is a potential energy thing. Right? Like magnetic attractions, that's potential. They're not moving. It's not where its height is. It's just saying stored potential energy is changing based on those attractions forming or weakening. So that's where the energy is being used. The energy is being used in this case to weaken attractions in the form of potential energy. When we get back to the liquid part, now yes, we're heating up the liquid. We're getting the particles to go faster. We're going from a cold liquid to a warmer liquid, right? Until again we get to the point where we are ready to break the intermolecular forces, where that energy being added is altering the potential energy of your substance. And then finally, if we were collecting the gas and containing it to heat up, we could make it go faster, which means we're changing its kinetic energy. So energy being added the whole time, but how that energy is being used is different. Like where it's going into, what it's being transferred into. Here it's getting transferred into kinetic energy, right? When the temperature is going up, but when the temperature is not changing, it's because the heat's being used, it's getting put into potential energy, right? Hey, guess what? Boiling. Boiling is actually not really about temperature. Yes, we say water boils at 100 degrees Celsius, but on Monday, I'm going to make it boil at 70 degrees Celsius. I'm going to do it. Because boiling is only indirectly related to temperature. We report the temperature, but that's not really what determines when it boils. So let's get a real definition for boiling here. The boiling point is the temperature at which the vapor pressure of a liquid equals the atmospheric pressure. The boiling point is the temperature at which the vapor pressure of a liquid equals the atmospheric pressure. So yeah, I know we report it as a temperature, but it just happens to be a temperature where something else is true, right? So if I can get that to be true at a different temperature, then the boiling point would be a different temperature. And what has to be true are that these two pressures have to be equal, okay? We're going to talk about pressure more next unit. So for right now, you just need to know that the definition is when those two pressures are equal. I'm not going to test you on what those pressures are, but I do want to give you a little bit of background. Atmospheric pressure would just be the pressure like in this room right now. When you're walking around in your environment, your atmosphere, what's the pressure? Vapor pressure, though, comes specifically from your liquid, because some of its molecules are turning into vapor, and then they're creating their own pressure. So vapor pressure is pressure caused by the liquid. Atmospheric pressure is just pressure in your room. And when you get those two equal, your substance will boil, right? So why do we talk about temperature then? Well, guess what? Temperature is a really easy way to change the vapor pressure of this liquid. If I heat up this liquid, I increase its vapor pressure. So when I say, hey, I'm going to get this water to boil, I'm going to heat it to 100, what I'm saying is I'm going to get this water's vapor pressure up to match the atmospheric pressure, and that happens to be at 100 degrees Celsius. At 100 degrees, the vapor pressure of water will now match the atmospheric pressure of this room. So when I get this thing to boil on Monday, I'm only going to get it to 70. I'm not going to get the vapor pressure up to the atmospheric pressure. What I'm going to do, I'm going to drop the atmospheric pressure. That's usually really hard to do, guys. Like, nobody at home can change the atmospheric pressure of their house, right? We can change this easily. Put it on the stove. We can change its vapor pressure. We can't change the pressure of the atmosphere without special science equipment, which I have. So I'll do that.